The Eclipse Predictions. The 2025 study of the Dresden Codex revealed eclipse prediction tables that maintain 33-minute accuracy across 5 centuries. These tables track 69 eclipse events between 755 and 1255 AD, with each entry noting duration, visibility, and celestial context. The records account for the 177-day eclipse season cycle and include corrections for the moon's wobble, its 18.6-year nodal regression. Modern astronomers confirm this adjustment requires tracking lunar orbital variations invisible without precision instruments. The Codex employs a 3-part prediction system like solving a celestial puzzle. Initial calculations use the 173.31-day interval between eclipse seasons. Building upon this foundation, secondary adjustments account for the moon's elliptical orbit, varying predictions by up to 12 hours. The final layer incorporates long-term nodal drift, ensuring century-spanning consistency. This layered approach matches modern eclipse computation methods, though the Maya achieved it 1,200 years earlier. NASA's 2025 analysis tested the table's predictive capacity. Using the Maya system as written, researchers projected eclipses forward 1,000 years from the Codex's creation date. The results matched 87% of actual eclipses within 2 hours, a revolutionary precision that outperformed medieval European predictions by significant margins. This accuracy was particularly striking for lunar eclipses, with 92% correct forecasts for events visible in Mesoamerica. The eclipse pages contain unexpected technical details. One column tracks the moon's velocity changes using base 5 fractions of a day. Another calculates shadow cone dimensions for solar eclipses, noting where totality would occur. These measurements required knowledge of lunar parallax, the apparent position shift when viewing the moon from different Earth locations. Processing these calculations manually would challenge modern astronomers. The Maya performed them using a combination of lookup tables and arithmetic in their base 20 system. A single eclipse prediction required 47 computational steps, including 7 multiplication operations with numbers up to 15 digits in length. Scribes made few errors. Cross-checking shows less than 1% calculation mistakes across the entire codex. The 2025 discoveries include a previously unknown eclipse verification method. Excavations at Uxmal uncovered 28 stone markers recording observed eclipses between 900 and 1100 AD. Each marker's position corresponds to the eclipse's magnitude and duration when viewed from a central platform. The arrangement forms a physical database matching codex records, suggesting observational cross-verification of predictions. The Dresden Codex's eclipse pages also track planetary positions during events. 8 solar eclipses note Venus's visibility and phase. 15 lunar eclipse records include Mars's position relative to the ecliptic. These dual observations required coordinating 2 separate calendrical systems, the 584-day Venus cycle and the 780-day Mars cycle, with eclipse periods. Recent translations explain the computational methods. Glyphs describe adjustments for the Saros cycle's gradual drift and nodal period calculations. These technical explanations appear alongside ritual instructions, blending astronomy and religion seamlessly. The predictions served practical purposes beyond ceremony. Agricultural almanacs link eclipse dates to planting cycles, noting soil moisture changes preceding events. Trade records show market suspensions during predicted eclipses. At Köppen, archaeologists found merchant contracts with penalty clauses for deliveries scheduled during eclipse periods. The system's accuracy implies generations of observational data. Tracking the 18-year Saros cycle requires at least 54 years to observe 3 repetitions. Accounting for nodal regression demands 150-plus years of records. The Maya apparently maintained unbroken astronomical observation for centuries, though no intermediate records survive. 2025 excavations at Mayapan uncovered a possible training facility. A chamber beneath the observatory contained practice tablets with eclipse calculations. These show students progressing from basic interval counting to full nodal corrections across 30 lesson stages. The facility's location implies formal astronomical education connected to state functions. Modern technology reveals subtle codex details. Multispectral imaging detected erased calculations beneath final entries, proving scribes made and corrected initial drafts. Some pages contain microscopic pigment variations indicating multiple authorship over generations. These findings confirm the tables resulted from accumulated knowledge, not sudden inspiration. The tables also aided celestial navigation. Several eclipse entries note simultaneous star positions, creating fixed references for travelers. A 2025 experiment using these markers enabled accurate longitude determination, a technique Europeans wouldn't develop until the 18th century. Maya traders potentially navigated coastal routes using these methods. Eclipse records influence Maya architecture. At Edzna, the Temple of the Five Stories aligns to cast shadows marking Saros cycle intervals. Chichen Itza's El Caracol contains window arrangements that frame eclipse-related celestial events. These structures physically embody the computational knowledge in the Dresden Codex. Surviving Maya communities preserve eclipse traditions. In 2025, anthropologists documented Lacandan elders predicting a lunar eclipse using methods matching the Codex tables. Their oral instructions yielded times within 45 minutes of NASA forecasts, closer than most modern almanacs achieved before computer calculations. The tables stand as testament to sustained scientific inquiry. Maintaining such accurate records across centuries required institutional continuity and dedicated observer lineages. The Codex represents not just astronomical knowledge, but a systematic approach to understanding cosmic order. The Jungle Metropolis.